Remember last time when I said, ooh, can you visualize this with me? In a spiral galaxy, there's this instability that causes the orbits to have their major axes systematically kind of misaligned. And the stars and gas and dust moving on their orbits will pass through the spiral arms. Some of them might be moving slower and the spiral arms catch up to them, but usually if they're moving faster and they pass through the spiral arms, and the whole thing spins at the global angular pattern speed. And I said, if only I had an animation to illustrate this. And apparently Estelle said, sounds like a challenge. And now I have an animation to illustrate this, as a matter of fact, thanks to Estelle. Check this out. Courtesy of Python, right? Check this out. Look at that. Ooh. Ah. You better than that. 1, 2, 3. Ooh. There we go, right? So you can see that you got things moving along the oval orbits there. And the whole pattern is systematically spinning around at the same time everything is moving along the orbits. And so they naturally bunch up where the orbits come together and make spiral arms that are slowly drifting around the center of the galaxy as the whole pattern spins around at the, what's it called? The speed. It's omega GP, the global angular pattern speed. The global angular pattern speed is the angular velocity that the major axes are drifting around at. That's the global angular pattern speed, as opposed to the angular speeds of the stars, gas, and dust moving their orbits, which is different from that. So the spiral arms are going around the center at the global angular pattern speed, while the stars, gas, and dust are moving at different speeds, able to catch up to the spiral arms, so to speak, but it's really just them bunching together where their orbits come together. So I'm actually going to post this to the Astro Learner group. It's a Google group of faculty that teach astronomy, and I bet other people can make use of this too. And I'm going to be using this in Astronomy 111 for sure when I talk about spiral galaxies and so forth. So thank you, Estelle.
No problem.
Indeed. All right. Yeah. Right. No applause, just cash. Okay. All righty. So, last time we were speaking about standard candles, right? Objects whose luminosity we somehow already know. And that means that if we can observe their apparent brightness, their apparent magnitude, and we already know their absolute magnitude, we can use the magnitude distance relation to calculate how far away they are from us. And this is how we measure intergalactic distances. There's just no other way around it, because we certainly can't use parallax for things that are in other galaxies. It's just way too far away for that. And we talked about how why there are these stars called Cepheid variables that are a very important standard candle, because the point representing a high mass star wanders back and forth in the upper right portion of the HR diagram after it leaves the main sequence, and sometimes it passes through the so-called instability strip, where it is unstable to pulsation. And then, here was the example of delta Cepheid, the prototype of the Cepheid variables. And Henrietta Swan Leavitt, awesome name. Every time I see her, I'm like, wow, what a name. They used to name people just. Henrietta Swan Leavitt discovered that there is a relationship that we now call Leavitt's law between the luminosity and the period of Cepheid variables. And so here's a plot, a modern plot, that shows the relation between period and luminosity. There's some scatter in the plot because it turns out that where a Cepheid is in the strip has an effect, a bit of an effect on its period for a given luminosity, and so it's not exactly one-to-one. Why, if you come and watch Isa's talk for senior research, you'll learn more about that. But still, on the whole, there's quite a good correlation between period and luminosity. And so that means if we can find, and they're very luminous, right? So this is, in terms of the sun's luminosity, 1,000, 3,000, 10,000, 30,000 solar luminosities. I didn't do the count, right? That's bright enough to see in other galaxies. And so you can find a Cepheid in some other galaxy, and you carefully measure that it's going from brightest to dimmest to brightest again every 30 days, and you look on your handy relationship here and you say, oh, it's a bit more than 10,000 times the sun's luminosity. You measure how bright it looks from Earth, and you can use the inverse square law, or more typically you would see what its absolute magnitude was, and use the magnitude-distance relation, which is the inverse square law written in terms of magnitudes, to find how far away it is. Now, up until the 1920s, there was a debate amongst astronomers, some of whom thought that the Milky Way was the galaxy in an otherwise, I guess, empty universe. Others of whom argued that no, the so-called spiral nebulae aren't in our galaxy. They are other island universes, as Immanuel Kant called them, other systems of stars comparable to our own Milky Way, way far away. And Edwin Hubble, the famous Edwin Hubble, settled the debate once and for all by observing the Andromeda Galaxy. This is the most distant object that can be readily observed with the naked eye. M33 in our local group is, I think, also just barely visible under really great conditions. But the Andromeda Galaxy under dark skies is quite easy to see. It looks like a little detached piece of the Milky Way, so to speak, a little fuzz patch. And so Edwin Hubble said, you know what? If I could find Cepheid variables in the Andromeda Galaxy, I could determine how far away it is, and determine, is it close enough to us to be part of our galaxy, or is it too far away from us to be part of our galaxy? Well, here is the very first Cepheid that Hubble identified in the Andromeda Galaxy. So he found one. And this is modern Hubble Space Telescope photographs of it, modern as in 2010, 2011. Yeah, that's still modern, right? You were alive, therefore it's modern, right? You probably were not as good at calculus back then, for example, but still, I was comparable in my current abilities back then, but still. Here it is. I love the original photograph, probably should have included it here because on there, Hubble had identified the star, and he'd written N next to it, because he was also seeing nova explosions. You see them within other galaxies, and so you see some stars that just brighten for a while, and then fade away, and don't get bright again, or novae, white dwarfs with nuclear eruptions on their surfaces in binary star systems. But then he crosses out N and writes VAR exclamation point, because no, it started getting brighter again after it got dimmest. And he's like, it's a Cepheid variable, it's what I've been looking for. And I just love that he was so excited that he, VAR exclamation point, right? He was just like, oh my God, I've done it, I found a Cepheid variable, and here it is. You can actually see that it's getting brighter and dimmer between December 17th and January 26th of 2011. In Hubble's notebook, you can see him, he plots the brightness of the star and gets its period, and based on the period luminosity relation that Henry Leavitt discovered, he says, okay, that Cepheid variable, and therefore the Andromeda Nebula, quote unquote, is 700,000 light years away. And because the Milky Way is like 100,000 light years across, it's too far away to be part of our galaxy. And so, ta-da! The people that said that there are island universes, that the Milky Way is just one of many galaxies in the universe, were right, and Edwin Hubble showed that. Now, his distance was off by a bit. The modern value is 2.5 million light years to the Andromeda Galaxy. So let's think about how far that is compared to the size of our own galaxy. Wait, tell me, how wide is our galaxy, the disk of our galaxy? 100,000 light years. That times what is 2.5 million light years? Well, 2.5 million years is 2,500,000 light years, right? So the Andromeda Galaxy is about 25 times further away than the size of our galaxy. And so if you represent our galaxy with a disk that would be a foot wide, or 30 centimeters for those of you who think in metric, who have the good fortune to think in metric. So here's the disk of our galaxy. The Andromeda Galaxy is about 150,000 light years across, somewhat here. And it's in the back of the room, because the back of the room is around 25 feet from us. It's a little bit further than that. The back row. Somebody in the back row holding up a little model of the Andromeda Galaxy and me holding up a model of the Milky Way would have their separation relative to one another just about right. Notice I mentioned before that if the sun was like a tennis ball, the nearest stars are like in Chicago from here. So stars within a galaxy are much further apart compared to their sizes than galaxies are compared to their sizes. Now obviously galaxies in absolute terms are much further apart than stars are, duh. But in terms of their own sizes, galaxies are much more crowded together than stars are. They're not nearly as far apart compared to their own sizes as stars are, and has significance because while stars would virtually never collide with one another, even if two galaxies pass through one another, the stars are so far apart compared to their sizes, very rarely would two stars collide. Galaxies collide all the time because they're not that far apart compared to how large they are, and they used to be closer together because the universe is expanding. So hold that thought. Hubble got 700,000 light years because it turns out that, and they didn't know this at the time until 1948, there are two classes of Cepheid variables. And the period luminosity law, Leavitt's law, had been calibrated with a different type of Cepheid, a type 2 Cepheid, than the ones that are in the disks of galaxies, type 1 Cepheids. And type 2 Cepheids are about 4 times dimmer for the same period as type 1 Cepheids are. So the star that Hubble was observing was like 4 times brighter than he thought it was, 4 times more luminous than he thought it was. And that means that for a given magnitude, it was a lot further away than he thought it was. And so part of the answer being wrong was that calibration wasn't as good back then, even for that type of Cepheid. But essentially, the universe, if you will, doubled in size in 1948. Not really, but our mental conception of it did, because all of a sudden we realized all these Cepheid variables we're using to determine distances to galaxies are 4 times brighter than we thought we were. And that means that they're twice as far away, right, from the inverse square law. If you move something twice as far away, it would look 4 times dimmer than otherwise. So put it the other way around, I'm looking at some star in a distant galaxy. I think it has a certain absolute magnitude. Based on that, I think it has a certain distance. But if it's really 4 times more luminous than I think it is, I have to move it twice as far away to make it have the brightness that it would have at my original distance if it was the other type of Cepheid. And so in 1948, Walter Baade published this result, and so all of a sudden the universe doubled in size, so to speak, our mental conception of it, because the stars were 4 times brighter than we thought we were, that we were using to find galaxy distances. This solved a mystery because it seemed like the Milky Way was like the biggest galaxy in the universe, which seemed kind of unlikely. It seemed like the Milky Way was bigger than the Andromeda Galaxy and every other galaxy that we measured. But on the other hand, if it's twice as far away as we thought it was for a given angular size, that means it's got twice the diameter that we thought it had as well. Every galaxy all of a sudden had twice this physical size that we thought it had before. And that bumped up the Andromeda Galaxy from being smaller than the Milky Way to bigger than the Milky Way. And then the other galaxies now, oh, they're bigger than the Milky Way. We had it wrong. The Milky Way is a giant spiral. It's kind of top tier among spirals. It's bigger than most spirals, but it's not the biggest. And this showed that. So, fun fact there. What questions do you have at this point? Yes?
Could we revisit what Cepheids are?
So Cepheids are stars which have left the main sequence, okay? So they're no longer using hydrogen in their cores. And that means that they're no longer on the main sequence. When you run the computer models, they do this business. And remember, let's see, a star is a balance between the inward pull of and the outward push of. And in a stable star like the sun, those are almost perfectly balanced. And so the star just says, I'll just hang out being a certain size. Right? It slowly changes over the nuclear timescale because of the changing amount of helium in the core and reduction in hydrogen. We know that the sun slowly brightens on the main sequence. But stars in the instability strip, it turns out, rapidly cycle between pressure being stronger than gravity and gravity being stronger than pressure related to their ionization zones. And as a result of that, they are pulsationally unstable. They vary in size and luminosity on a regular basis, rhythmically. And furthermore, and so that's what's happening here. Furthermore, and I should have said this before, the more luminous the star, well, what does that imply? And we really have to say it's average luminosity because it's variable, but the more luminous the star, what does that imply about the mass of the star? Well, they're coming from higher and higher up on the main sequence before they do this business. So as I move up the main sequence, what's happening to the masses of the stars? Are they getting bigger or smaller as I go up the main sequence? They're getting bigger. So a more luminous Cepheid, because they keep nearly constant luminosities after they leave the main sequence, they expand, but their surface temperature cools at just the right amount that the luminosity stays pretty almost constant. So more luminous Cepheids are also more massive Cepheids. Pulsation is sort of like ringing. So if I ring a bell, here's a big bell, here's a little bell, right? I'm going to hit the little bell, I'm going to hit the big bell. Which one goes ding, and which one goes boom, right here, and which one goes boom? The big one goes boom, and the little one goes ding, right? Okay? So more massive stars have more mass you need to throw around in these oscillations, and so they pulsate more slowly with longer periods than less massive stars. But because the more massive ones are also more luminous, and because it's the luminosity that we can directly observe, then we say that there's this relation between the luminosity and the period. More fundamentally, it's a relationship between the mass and the period, but you can't directly observe the mass. And so A star with a longer period is a more massive star, and therefore also a more luminous star that is ringing slower, so to speak. Now, 100 days, I can't hear something with a frequency with a period of 100 days with a sound wave, but it's the same principle. So, does that help?
Absolutely.
Okay. Alrighty. What other questions do you have? Alrighty. So, Hubble says, great! I have shown that the Andromeda Galaxy and other spiral nebulae are separate systems of stars. Island universes, as Immanuel Kant, the philosopher, would say. And the Milky Way is just one of many galaxies in the universe. Now we know that there are hundreds of billions of galaxies in the observable universe, and our sun is one of hundreds of billions of stars in our galaxy. In fact, run the numbers, right? If you assume there's like 10 to the 11th stars in a galaxy and 10 to the 11th 100 billion galaxies in the observable universe, that's like roughly 10 to the 22nd power stars in the observable universe, which is also roughly the number of grains of sand on all the beaches of Earth combined. It just happens that the number of stars in the observable universe and the number of sand grains on all of Earth's beaches, it's a comparable number. A little fun fact that's in the intro astronomy textbook. Nice little things like that. Well, Vesto Slipher, before Hubble did this work, had shown that the spiral nebulae appeared to be systematically redshifted if you looked at their spectral lines. Now, the spectral lines are going to be from the combined light of the many stars in the galaxy, but stars have overall fairly similar spectra to one another. There's a lot of differences, that's why we classify them, but yeah, stars all have hydrogen lines, etc., etc. And so a whole galaxy of stars, you'll be able to see hydrogen lines, the Balmer series hydrogen lines, in the combined spectrum of all those stars. And so we can use that to compare the wavelengths we measure for the galaxy's hydrogen lines, or whatever lines we're using, to ones in the laboratory to figure out how fast the galaxy is moving towards or away from us. Well, Vesto Slipher looked at spectra of spiral nebulae. For all he knew, they were part of the Milky Way. For this argument, it doesn't matter. If they're all systematically, almost all of them are redshifted, what does that imply about their motion relative to us? If they're redshifted, moving towards us or moving away from us? Moving away from us, right? Because moving away stretches out the wavelengths. And so it seemed that the spiral nebulae were systematically moving away from us. So if you think they're part of the Milky Way, for some reason, they're moving away from the center of the Milky Way. Hubble said, well, let me explore this further, because, I mean, we know that the spiral nebulae appear to be systematically moving away from us. Let's gather the data and see what it tells us. So here's just an illustration of the idea of absorption lines in the nearby star appear, well, not, it says they're rest wavelengths. Well, that would only be if it were really at rest with respect to us. If it's moving, they would be either red shifted or blue shifted. Here's a galaxy with a recession speed. These are 7,600 kilometers per second. It's getting further away from us at a rate of 7,600 kilometers per second. That's going to systematically redshift the spectral lines to longer wavelengths. So, for example, here's good old H alpha, the lovely ruby deep red spectral line of hydrogen. Okay, it's black here because it's an absorption line. Shut up. The light around it is that lovely red color. Why? That absorption line happens when a hydrogen, really lots of hydrogen atoms, are jumping from n equals what to n equals what? That's Lyman alpha. That's the ultraviolet Lyman alpha line. ground state 10 equals 2. Now this is
2 to 3?
2 to 3, yeah, this is 2 to 3. Hydrogen beta, the lovely teal line, is the absorption line when electrons go from, 2 to 4. Hydrogen gamma is certainly not indigo, but if it were, I'd have to spit on it. Now, hydrogen gamma, H gamma, is the transition from 2 to 5, and hydrogen delta, also not indigo for sure, bluish purple maybe, goes 2 to 6. 2 to 7 is in the ultraviolet, 2 to 8 is in the ultraviolet, near ultraviolet. So there's these 4 spectral lines of hydrogen. Well, the rest wavelength of H alpha, 656.3 nanometers. In that galaxy, it's observed at 672.9 nanometers. H beta is at a longer wavelength. Gamma, and they're all the delta lambda over lambda is all consistent with that speed of 7,600 kilometers per second when we plug it into the Doppler shift formula. So Hubble said, well, let me use Cepheids now to measure the distances to a lot of other galaxies, and I'll look at their recession speeds, and I'll make a plot, and I'll see if I find anything systematic. Here's Hubble's original plot. He found something systematic. The further away the galaxy is, the faster it's moving away from us. This is the famous Hubble redshift distance relation, the Hubble law. The reason that one of the primary motivations of launching the Hubble Space Telescope was to be able to observe Cepheids in more distant galaxies than you can see from the ground because of atmospheric interference, and to get a more precise determination of the so-called Hubble constant that we'll be talking about. So here's a modern plot. This little rectangle right there is what Hubble did. So we've extended it a bit since then. And since this is from my intro astronomy textbook, where people more intuitively think in terms of light years than they do in terms of parsecs, then the distance is plotted in mega light years, millions of light years, and the recession speed is plotted in kilometers per second. And notice you get a pretty good fit to a straight line there. And the slope of that line is called the Hubble constant, quote unquote, H naught is called. And it works out to be 22 kilometers per second per mega light year in these units. But astronomers typically use megaparsecs instead of mega light years. And in those units, it's closer to like 68 kilometers per second per megaparsec. So if you think about this, we've got the straight line relationship, right? It's all plotted straight line relationships, linear relationships, out the wazoo, as they say in lab and so forth. And so if I have, I guess I should put the camera over there. If I have a plot where I've got D on the horizontal axis and V sub R, the recession speed on the vertical axis. And, okay, here's my fake data. Fake data, you always have to have some above and some below. Here's my fake data, okay. And the slope of that. And the intercept, what's the y-intercept? Looks like to be about 0, right? So the y-intercept, there's 0. I mean, after all, we're not receding from ourselves. So the figure goes through 0. So there's a linear relationship. What linear relationship is this representing? It says what equals what times what. Yeah, so y equals mx plus b, where b is the intercept and m is the slope, right? So here I'm going to write this, but what is my y variable? B sub r equals the slope h naught times the x variable, which is d, right? This is the Hubble redshift distance relation. Really, it's like a velocity distance relation. We typically call it the Hubble redshift distance relation. And h naught is the quote-unquote Hubble constant. Except it's only constant in space at a given time. It's not constant in time. It changes over time as the universe ages. Its value changes. So the Hubble parameter, right? We always get this like terminology that can be a little bit, but anyway, the Hubble parameter is h as a function of time. So if we made this plot when the universe was younger, the slope would have been different. And h of t is the slope of the plot like this that you would make when the universe's age is t. T equals t naught is the present time, present age of the universe. And you might say, like, you mean today, or yesterday, or tomorrow, or 100 years ago? Does it matter? How old's the universe? 13.8 billion years, right? So if I made 1,000 years ago, do you think T naught has really changed significantly? No. Right? In other words, now has plenty of wiggle room because even 1,000 years is a tiny fraction of the age of the universe. So T equals T naught is the present age of the universe, and don't worry about, you mean at noon tomorrow? Right? No. Shut up, right? And so what we're saying then is that H naught, by definition, is H evaluated at time T naught. It's H now, which is present value of H. So H naught is constant in space. It has the same values, essentially. It's going to be very local variations, but overall, same value everywhere in the universe at a given time. It's constant in space, and H naught, the Hubble constant, is its current value, and the time variable h of t is the Hubble parameter. So in other words, the Hubble constant is the current value of the Hubble parameter, is what it comes down to. Does that make sense? The Hubble constant is the current value of the Hubble parameter. Questions, comments, observations? The Hubble constant is the current value of the Hubble parameter. It sounds like a mantra, right? The Hubble constant is the current value of the Hubble parameter. The Hubble constant is the current value of the Hubble parameter, and so on and so forth. Right? Well, does this mean that the Milky Way smells terrible and all the other galaxies are trying to get away from it? Does it mean that the Milky Way galaxy is the center of a universal expansion? Everything is flying away from the Milky Way, Trying to get away from it? Yeah, most of you know. No, that is not what it means. So let's talk about that. Before I came to teach at our hallowed university, I taught at Randolph-Macon College in Ashland, Virginia. Okay, it's a lovely place. And they're not really, we don't tend to get applicants to our fine institution who also apply to theirs. So they're not really in competition with us. So it's okay to love them, isn't that right? Yes. So I taught at Randolph-Macon College in Ashland, Virginia. And it's kind of funny because Ashland, Virginia is one county north of the state capital, Richmond, just like Delaware is one county north of the state capital, Columbus. So I have a thing for teaching at small colleges, one county north of state capitals, apparently. And this was before I was there. One of their town council members had taken the Astronomy 101 course at Randolph-Macon College and learned that no matter what galaxy you're in, all the galaxies seem to be moving away from you, well, with a few exceptions. Like the Andromeda Galaxy turns out moving towards us, but that's because it's close enough that its motion through space overcomes it being carried away from us by the expansion of space. Okay, I spoiled the punchline, but you probably know that already. Okay, so every galaxy, it looks like you're the center of the universe and everybody's running away from you, so to speak. And so everybody gets to say, and really the universe doesn't have a center. Well, that means everybody can kind of decide that they're the center of the universe. And so the town councilman thought this would make a great town motto, and they actually adopted it. The town motto of Ashland, Virginia is Ashland, Virginia, the center of the universe. And this is an actual sign that they put up along Main Street or whatever. And so they just really went for it. Ashland's the center of the universe. I mean, we can't lie, here it is on our signs and so forth. But every galaxy gets to kind of claim, well, it looks to us like we're the center of the universe. My sister-in-law was born on July 4th, and when she was a little girl, you guessed it, she thought that all those July 4th fireworks were for celebrating her birthday, right? Because kids think they're the center of the universe. Kids born on Christmas sometimes think for a while that it's all about them, that everybody's celebrating their birthday. It's amazing you can think that when you're that young. Well, you're the center of your parents' universe, and so why not everybody else's universe too, right? Ashland's got the same complex, apparently. It's all about us. But that's not what happens. Yeah, rules E. Cough drop addiction going on here. Okay. I get choked up about this, right? It just never gets old, I tell you. So it never gets old when I say, I'm all no, you need baby. And my wife, you see the mail, right? Never gets old. Anyway, according to me. And she's like, wow, you have such a big head. And I say, no, I'm actually humble. And she's like, oh, come on, how's that humble? I say, my humility is just one of my many outstanding qualities, right? So, all right, anyway, I actually am humble, so don't. Anyway, it is a natural consequence of general relativity that the universe should be expanding or contracting. And in fact, Einstein saw that drop out of the equations, and he thought, well, that can't be right. He thought the universe should be static, neither expanding nor contracting. And he added a term to his equations, the cosmological constant, to counteract that and have the universe maintain a constant size, as it were. And then Hubble comes along and shows that the universe is expanding. And so Einstein's like, well, he's German, so he's probably like, Scheiße! Like, ah! I could have predicted that, and kind of did predict it, but in other words, it turns out that he was right, and he didn't really need that extra term. It will also turn out, as we say, that now we think the expansion of the universe is accelerating, and the simplest way to account for that is to add a cosmological constant to the equations of general relativity in order to produce the necessary sort of anti-gravity to make that happen. So Einstein had a knack for being right even when he was wrong, as it were. But back to our story, the typical analogy that's made is, for example, an expanding rubber sheet. So the rubber sheet represents the expansion of space over time. And we need this to be an infinitely stretchy rubber sheet so it doesn't snap on us. But imagine a rubber sheet, and you put coins on the rubber sheet to represent galaxies. And this is especially nice because will the coins get bigger as the sheet gets bigger? No. And in fact, galaxies don't expand as the universe expands because something that's held together by its own gravity or by other internal forces does not expand with the rest of the universe. Those internal forces prevent that from happening. So sometimes people think maybe your body's getting slowly bigger as the universe expands. And it's not. And Earth doesn't expand, and the Milky Way doesn't expand. It's the spaces between the galaxies that are expanding, and that's captured with this analogy too, because the coins don't expand. And so imagine that there's a cute little ant. There's Aunt Matilda, there's Aunt Hillary, I think we had Aunt Tommy in there somewhere, or Tommy was in there somewhere, Aunt Murgatroyd, I don't know, whatever. And they're all watching. The sheet keeps expanding, the sheet keeps stretching. Is it not true that every coin gets further away from every other coin? So every ant's going to say, all the other coins are moving away from me. And it's not that the coins are flying through space away from it. They're not flying along the rubber sheet. It's that the rubber itself is expanding and carrying all the coins further away from one another. And that's what's happening in the universe. The space between clusters of galaxies is expanding, carrying them away from one another. So it's not motion of the galaxies through space, if you will, that's responsible for the Hubble redshift distance relation. It's the expansion of space that is causing it. And here's the 3D version, galaxies in space. Okay, now we have to expand in every direction. But the idea is still the same. And furthermore, you get this relation that the further away a galaxy is, the faster it's moving away from us, the faster its distance is increasing from us, because simply the more space there is between us and another galaxy, the more space there is that is expanding between us and another galaxy. So more distant galaxies move away faster because there's more space between us and them that is busy expanding. And so these ants would see a Hubble redshift distance relation. The speed of another coin moving away from them would be twice as fast if the coin was twice as far, because there would be twice as much rubber stretching between them and the other coin. To be specific, here's a model of all that. So imagine that miraculously galaxies are spread out on a rectangular grid. Or a square grid, right? So it's a graph paper universe, and here's a bunch of galaxies, A, B, C, D, E, that start out with 100 megaparsecs between adjacent galaxies. Now this 100 megaparsecs is much larger than a galaxy, so these are exaggerated in size, but whatever, it doesn't matter. Okay, so at one point, the galaxies, there's 100 megaparsecs between successive galaxies, as it were. Now you stretch the whole universe so that the grid spacing becomes 150 megaparsecs instead of 100 megaparsecs. Okay? And I can't exactly, okay, I'm hiding it so you can't see it, and then we'll slowly reveal it as we go along. But anyway, why? What's the original distance between A and B? 100 megaparsecs. Between A and C? 200
200.
200 between A and D, 300 between A and E,
100.
100. What's the final distance between A and B?
150.
150. What's the final distance between A and C?
300.
300 between A and D.
450.
450, 3 times 150. Between A and E?
150.
150, okay. So let's look at how much the distance has changed. A to B changed from 100 to 100. 250 megaparsecs for a total change of 50 megaparsecs. A to C went from 200 to 300 for a change of 100 megaparsecs. A to D went from 300 to 450 for a change of 150 megaparsecs. A to E is just a repetition of A to B. 100 went to 150, so 50 megaparsecs. The point being, A and C are twice as far apart as A and B, and the distance between them also changed twice as much in that same interval. A and D are 3 times as farther apart at all times than are A and B, and the distance between them changed 3 times as much, 150 versus 50, during that interval. So if a galaxy is factor times further away, the distance changes by exactly that same factor compared to a galaxy which is not factor times further away, so to speak. So this is why there's a Hubble redshift distance relation. It's just that the further away 2 galaxies are, the more space is stretching between them. Such that doubling the distance doubles the speed of recession. Quintupling the distance quintuples the speed of recession. Making the distance 7.474 times bigger makes the recession speed 7.47 times larger, etc., etc., etc. That's the big picture here. What questions do you have? Okay. Yeah, okay, so we'll take a break right here and explain why that also means photons get stretched out as the universe expands. And that's what's actually causing the redshift. It's not a Doppler shift motion through space redshift. It's redshift caused by the expansion of space. It is a cosmological redshift. Back to the sulfines. Back to the... Let's have more fun. Okay, more fun. So, why does the expansion of the universe stretch out the wavelengths of photons traveling through it? I like to make an analogy with 2 ants crawling along a balloon. So here's a balloon. There's a balloon. Wait, balloon. 1 L or 2? It's just 1. Right? 2? Is it 2 L's? Okay, I'll still make it remember. Okay, it's a ball. It's a balloon. And here is ant, let's make her Matilda. And here, that's Aunt Hillary. And Aunt Hillary and Aunt Matilda are both crawling along the surface of the balloon at exactly the same speed, v. And the balloon is not being inflated, it's just chilling out, being its balloony self. 2 ants crawling along. And they're going to go in the same direction. At the same speed v. So the distance between them What about the distance between our two ants crawling along at the same speed? Yeah, it's staying the same, right? Stays constant. That's ants in a non-inflating or non-expanding universe. But now let's start blowing up the balloon. But if the balloon is, I want you to imagine it steadily expanding. The distance between them now what? If the balloon is blowing up at the same time they're both crawling along at speed v, are they staying a constant distance apart? No. They're getting further apart because the rubber in between them is stretching out. As you blow up the balloon, the rubber is stretching. So even though they're both moving along the balloon surface at the same speed, the balloon itself is getting bigger and bigger, and so the ants are being carried apart because of that. The distance between them increases with time. Since the rubber between them is stretching. The rubber between them is stretching, so our ants are getting further apart now. Hillary, Hillary, you're moving away. Hillary, Hillary. Okay? So, now what we're going to do is replace the ants with successive crests of a wave of growth. Replace the ants with successive crests of a lake wave. Both crests move through space. At speed, how fast are those wave crests moving? If you got a bunch of meter sticks and clocks and measured how fast those crests are moving, what would you come up with? Yes, C. You would come up with C. Yes. C. At speed C, if the universe isn't expanding, the distance between the wave crests stays constant. But if the universe is expanding, even though both crests are moving through space at speed c, the space between them is expanding as the universe expands, and so the crests get further apart with time. In an expanding universe, the space between the crests is expanding so the distance between the crests increases. With time. But what we call the distance between the wave crests. That's the of the light wave. The distance between crests is its, what's that? Here's, okay, so here's crest. What's that distance between crests? That's the wavelength. That's the wavelength, right? That's the wavelength. The distance between crests is the wavelength. Why, if the crests are getting further apart, what's happening to the wavelength? It's increasing. So lambda is increasing. Lambda increases with time. Is that redshift or blue shift?
Redshift.
That's redshift, right? That's redshift. In other words, can I erase the blue now? Because I have limited space to write here. So, because I'm zoomed in here. In other words, we have cosmological redshift is what we call it. And that is what we're observing when we see galaxies redshifted. It's really cosmological redshift. It's the fact that photons increase in wavelength as they travel through an expanding universe. That's what we're seeing. It's not a Doppler shift. It's not in the classical sense, at least. It's not because other galaxies are moving away from us through space. Now, there can be a component of that, which is on top of this, but it's the expansion of space during the time that the photon is traveling to us that causes us to see this redshift. So, what takes longer to reach us? A photon traveling to us, and this is supposed to be a bit of a, duh. What takes longer to reach us? A photon coming to us from a nearby galaxy or a photon coming to us from a distant galaxy? Which one's going to take longer to reach us? The distant galaxy. That photon takes longer to reach us. And so the reason we see more redshift is because during its flight to us, there's been a longer time over which the photon's wavelength has been stretching. And so we see greater redshift for more distant galaxies, simply because the photons travel along getting redshifted for a longer amount of time. And so this is illustrating the idea. Here we see a yellow photon of light emitted long ago from a distant galaxy. As time passes, the photon stretches along with the expansion of the universe. The stretching makes the photon's wavelength longer, so it's redder in color when it reaches us in the Milky Way galaxy. But if the galaxy was originally over here, it takes longer for us to reach us. It's been stretching out for a longer time, and so the wavelength increases as a result of that compared to from a closer galaxy. What questions do you have? So you're sure you understand that's what the redshifts in the Hubble redshift distance relation, this is the way to think of stretching of photons as the universe expands.
Does this mean if like a galaxy is still coming towards us, it's still being redshifted?
So if there's two components to what we see in terms of the shift of a galaxy's photons. If they are just being carried along by the Hubble flow sort of passively. If you imagine that in this earlier figure, all the galaxies are just sitting there at the intersections of the grid, then what you're seeing is pure cosmological redshift. But in reality, there is some motion of galaxies relative to the grid lines, so to speak. And so that is added on top of the cosmological redshift. So the Andromeda galaxy is moving towards us at 90 kilometers per second because it's close enough to us that being carried away from us by the expansion of space is outdone by its motion toward us through space. And so we see a net Doppler shift from the Andromeda galaxy because it's, blue shift from the Andromeda galaxy because it's actually getting closer to us with time. Its motion through space overcomes the expansion of space. And that's part of the reason why there's scatter in a plot like that, a Hubble plot, is because, if you had perfect observations and there was just the so-called Hubble flow, all the galaxies are at rest with respect to the cosmic grid line, so to speak, well then you get a nice perfect straight line. But in reality, galaxies also have what we call peculiar velocities. Peculiar doesn't mean strange in this context. It just means unique to it, their own motion relative to the cosmic grid, if you will. And that's going to produce some scatter because that's some extra Doppler shift on top of the cosmological shift. Does that make sense?
Yeah.
That's the idea. Okay. Meanwhile, here's another thing to realize. When we talk about the distance to a galaxy, we got to be careful when we're in an expanding universe. Because when we talk about the distance to a faraway galaxy, well, one natural way to do it would be to use the inverse square law, right? But if you do that, if you just use the inverse square law, you get what's called the luminosity distance to the galaxy or other object. You're just basing it on the inverse square law for light. But wait a minute. Let's see. Here is a supernova happening long ago in a distant galaxy. They're so bright we can see them across the universe. As time passes, the universe expands and the distance to that galaxy is increasing. The galaxy's distance is therefore much greater when the supernova's light reaches us today in the Milky Way galaxy. And so if we are calculating the distance based on the inverse square law, well, there's a couple things in play, and we'll say more about this when we do the cosmology chapter. So if all there was the spreading out of the photons over larger and larger surfaces as they travel through the universe, well, then we would expect the luminosity distance to correspond to how far away the galaxy is now compared to when the light was emitted, but there's a complication. The photons are all getting redshifted, which is lowering the flux, lowering the brightness of the galaxy because the photons are all losing energy as a result of that. And so if we use the inverse square law based on if we use the inverse square law, we get neither directly the distance that the galaxy was when the light was emitted from us, nor do we get its present distance. We get something we call luminosity distance, which is neither of those things. So in other words, for now, just suffices to say that you have to be careful when you talk about the distance to a galaxy, because what distance do you mean exactly? Is it its present distance? Well, you can't directly measure that. You can't stretch out a meter stick between us and the other galaxy and figure out how far away it is. Is it how far away it was when the light was emitted? Is it what? What do you mean by the distance? So in an expanding universe, you got to think about that. What questions do you have? And we will think about that when we get to the next chapter after today. Next set of chapters. Okay. Let's see, where are we at here? When we look further out into space, we're also looking further back in time, right? So in principle, if you want to study galaxy evolution, how they change with time, well, just look deeper and deeper out in the universe, and you're seeing galaxies at younger and younger ages because they're further and further away. And so this is illustrating the basic idea there. So here is approximate look-back times in years. The look-back time is how long ago the light was emitted that we're receiving today. Here's the approximate age of the universe at the time the light was emitted in billions of years. And so here are ellipticals seen at look-back times that are relatively small, between 0 and 2 billion years ago. Here they are greater and greater look-back times, while we see ellipticals that are with look-back times of more than 8 billion years. And does it still look pretty much like an elliptical today? Seems the answer is yes, pretty much. Here's spirals. Here's a spiral with a look-back time of more than 8 billion years. Does that look pretty much like a spiral today? Pretty much. These studies tend to show us that galaxies formed and matured pretty early in the history of the universe. Now, there's another problem though. The further away you look in space, the lower the quality of your images, right? Because they're further away, they're dimmer, they're smaller in angular size. And so, okay, let's go back more than 10 billion years in look-back time. At that point, we find, oh, they don't look like modern galaxies anymore. And in general terms, this suggests that galaxies assembled from smaller fragments is what it comes down to. In the early universe, galaxies were closer together because the universe has been expanding, and so you run the clock backwards, everything is closer together. And so this suggests there's two big models of galaxy formation. One would be a top-down model where you get a giant cloud of gas that collapses to form a galaxy, similar to the way that an interstellar gas cloud collapses to form a star. And then there's a bottom-up approach where smaller fragments form first and then merge to create mature galaxies. And this suggests that that approach is probably the more accurate, that smaller proto-galaxies form first and then merge to form adult galaxies, so to speak. So the merger of small proto-galaxies is thought to play a role in the formation of large galaxies. We have galactic cannibalism. Galaxies are cannibals. They like eating other galaxies. We have ample evidence that our Milky Way is quite the cannibal. We see streams of stars that appear to be from galaxies that our Milky Way swallowed. It ate them. And so then the question is, well, why do we have ellipticals versus spirals? And so the angular momentum of a galaxy's protogalactic cloud system, because not one single giant cloud, the evidence is that there's lots of protogalactic clouds that make little cute galaxies, proto-galaxies that then merge. The angular momentum of a galaxy's protogalactic cloud system may determine whether it ends up spiral or elliptical. So in other words, a protogalactic cloud system that starts with little or no angular momentum relative to its mass, well then, it may be that it all just kind of collapses. It's not got enough angular momentum to flatten out into a disk, and so it ends up as an elliptical galaxy, more spherically distributed as a result of that. Whereas a protogalactic cloud system with more angular momentum will spin faster and faster as it contracts. Conservation of angular momentum. It will tend to form a disk as a result of that, ending up as a spiral galaxy. So that's one idea, is higher angular momentum makes spirals, lower angular momentum makes ellipticals. But it could be about the gas density too. A dense protogalactic cloud system may form its stars before it can settle into a disk. There's lots of material there, lots of star formation. Stars, let's go to these crazy orbits as we've been collapsing, and then by the time it's smaller, there's no gas and dust left over to make new stars, and so you end up as an elliptical galaxy as a result of that. Because remember, ellipticals don't have much star formation, whereas spirals do. Whereas gas in a less dense protogalactic cloud system forms stars more slowly, it's still settling, it makes a disk because of angular momentum conservation and the fact that it's easier to fall in perpendicular to the disk along the axis of rotation than perpendicular to it. It's kind of similar, like if I was holding a weight and my job is to pull it in towards myself, What's easier for me to pull in? This one, I'm going to try to pull this in, or this one, I'm going to try to pull that in. Which one's easier for me to pull in? The second one, right? And the same thing happens in a collapsing protostar, or here, a collapsing protogalaxy. It's easier for stuff to fall in perpendicular to the disk along the axis of rotation than within the plane of the disk, perpendicular to the axis of rotation. There's a sort of centrifugal repulsion, so to speak. And so, if it's less dense, it may have time to settle into a disk and end up as a spiral galaxy. This need not be an either or. It's probably a combination of how much angular momentum the protogalactic cloud system had and how dense it was that determines whether stars end up as galaxies end up as spirals or ellipticals. What questions do you have at this point? But you can also form ellipticals from spirals merging, because remember, galaxies are not so far apart from one another compared to their sizes. We are, front of the room, back of the room for the Andromeda and Milky Way galaxy, and in clusters of galaxies, galaxies are closer together than in our so-called local group, which is a relatively loose assemblage of galaxies. Deep in the hearts of clusters of galaxies, mergers and collisions are happening all the time. They're very common. They take hundreds of millions of years, right? So it's slow motion. But two simulated spiral galaxies approach each other on a collision course. The first encounter begins to disrupt the two galaxies and sends them into orbit around one another. This is a computer simulation this is based on. As the collision continues, much of the gas in the disk of each galaxy collapses towards the center. Gravitational forces between the two galaxies tear out long streamers of stars called tidal tails. The centers of the two galaxies approach one another and begin to merge, and the single galaxy resulting from the collision and merger is an elliptical galaxy surrounded by debris. Well, remember I said that the Andromeda galaxy is approaching us at about 90 kilometers per second? Now the question is, hi, you're the Milky Way galaxy and I'm the Andromeda galaxy, okay? Is it like this? Or is it like this? Because this would still be approaching, right? Are they going to miss or are they going to hit one another? So it's controversial, but very careful measurements of the sideways motion, because it's easy to measure Doppler shift to see how fast the galaxy is moving towards or away from us, generally away, not for the Andromeda galaxy, it's moving through space towards us. What's a lot harder to do is to measure the side-to-side motion, because that doesn't produce a Doppler shift, and that thing is friggin' 2.5 million light years away. So it's not moving very fast sideways relative to our line of sight. But careful measurements seem to indicate it's on a collision course. And in about 5 billion years, this is going to be the result.
Astronomers have used the Hubble Space Telescope to forecast a future cosmic pileup, the titanic collision of the Milky Way and the Andromeda Galaxy in about 4 billion years' time. The Andromeda Galaxy, some 2.2 million light years away, is the closest spiral galaxy to our home, the Milky Way. For around a century, astronomers have known that it's moving towards us, but whether or not the two galaxies would actually collide or simply fly past each other remained unclear. Now, a team of astronomers has used the Hubble Space Telescope to shed light on this question by looking at the motion of stars in the Andromeda Galaxy.
Okay, we wanted to figure out how Andromeda was moving through space. So in order to do that, we measured the location of the Andromeda stars relative to the background galaxies. In 2002, they were in one place, and in 2010, they were in a slightly different place. And that allowed us to measure the motion over a period of 8 years.
The motion is actually incredibly subtle and not obvious to the human eye, even when looking at Hubble's sharp images. However, sophisticated image analysis revealed tiny movements that the scientists were able to project into the future. Based on these findings, it is finally possible to show what will happen to the Milky Way over the next 8 billion years. As the galaxies drift closer, and then collide and gradually merge into a single, larger, elliptical galaxy with reddish stars. And yet the solar system should in fact survive this huge crash.
Now, the reason we think that our solar system will not be much affected by this collision between the Milky Way and Andromeda is that galaxies are actually mostly empty space. Even though our galaxy, as well as the Andromeda galaxy, has 100 billion stars in it, they're very far apart. So if two galaxies actually collide with each other, the stars basically pass right between each other. And the chance of two stars directly hitting each other is really, really small. So the likelihood that our solar system will be directly impacted by another star, for example in Andromeda, as we collide with it, is really, really small. Well, if life is still present on Earth when this happens, the changes in the sky will be quite spectacular. Now, they will be very, very slow, because the time scales on the scales of galaxies in the universe are very, very long. So you have to think millions of years. But even then, over these time scales of millions of years, we will see big changes. If we wait a few billion years, Andromeda will be huge on the sky. It will be as big as our Milky Way. It will be very close to it. And then later, when the galaxies merge, the merged remnant of the Milky Way galaxy and Andromeda will look more like an elliptical galaxy. And we will be sitting right in it. So the view of the Milky Way on the night sky will be completely gone. And this band of light will be replaced by a more spheroidal distribution of light.
And so the Sun, born in the Milky Way almost 5 billion years ago, will end its life in a new orbit as part of a new galaxy.
Crazy. Yes?
Are you also depressed you're not going to see the view of a giant galaxy in the sky at night?
Yes, I guess I could say that. But,
How cool would that be?
but it would, yes. Yeah. But I've given up on this particular ambition, so I don't think I'll get
A couple billion years off, yeah.
Yeah, a couple billion years off, that's right, yeah.
Not so bad.
Some future civilizations have really cool.
That's right. I think I told you guys a joke about the scientist who's like, the two scientists, and one was like, my calculations have determined that the sun's going to become a red giant in 5 billion years, and all that. Did I tell you that joke? You did, yeah, I did, yeah, right. The punchline is, says it, they say it several times, and then the other scientist finally says, oh, thank God, I thought you said 5 million years. Right, yes. Okay, so, crazy. All right, so don't do that, okay? Here's some examples. There's a collision between two spiral galaxies that has stripped out two long tidal tails of stars. This is called the antennae. And notice that it kind of looks like an insect's head with antennae sticking out of it, which is why it's called the antennae. So these are the tidal tails because we've got two galaxies near one another. Thinking Newtonianly, the gravitational force from the other galaxy is stronger on the near side than it is on the far side, and that tidal difference in those forces strips out these tidal tails. The sun could conceivably be thrown into intergalactic space along one of those tidal tails. So we don't know exactly what will happen. But you get a huge burst of star formation because you've got all these GMCs and giant molecular clouds in the two galaxies colliding with one another. And that tends to use up the interstellar gas in the two galaxies in a violent burst of star formation, which is why it turns into an elliptical too in the end. Because you make a time lapse, right? There's all star formation, and then it's like, ooh, pretty! Look at all those supernovae. Of course, I'm very big time lapse there. Pop, 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 pop. It's like you're in the microwave, right? Wait till there's 2 seconds between pops. Wait till there's 20 million years between explosions, right, or something. Yeah, that might be more than that. Eventually what you got is a system where there's no young stars anymore. And the brightest stars are old red giants and elliptical with no interstellar gas and dust. It got used up in this burst of star formation when they emerged. Yes?
How would the number of stars compare before and after emerging?
So, most of the stars that will be born in our galaxy have already been born, it turns out. Same in Andromeda. The amount of stars, the amount of gas and dust left isn't enough to make as many stars as already are there. So the answer is there'll definitely be more stars. Look at that. But it's not going to be a huge additional number compared to what's already there. Yes?
You mentioned that some of them got flung out in those tails of the
tails.
stars. Like how much of the galaxy would be like lost to that, and like also like how common is it for like stars and such to not be connected to like a galaxy?
So, one is, I don't think it's a lot of the maps. Like you watch that simulation, right? It mostly stayed in the middle. And a lot of the tidal tails can end up being like, oh, I'm coming back again, you know, and so you made it. But some of the stars might be flung out at fast escape speed and just keep on going. I don't think we know the answer to how many stars out there are rogue stars in intergalactic space because you can't see them, you know, it's just too dim to see a low mass star that got flung into intergalactic space. I don't know the answer to that question, but it's probably a fairly small number that would be like that. That'd be lonely. Just being a lonely star in intergalactic space. That's exactly. I'm so lonely. I want to be in a galaxy. Yes.
So, isn't there like black holes with the galaxy?
Yeah, so the halo of our galaxy has black holes.
So like, couldn't it be that some of the black holes are from stars that we call
Well, what I'm talking about here, because the black holes we can see are ones that are in the halo of our galaxy, and those would generally be high mass halo stars that just became black holes in the usual way, I think. Yeah. Here's a cool example. NGC 474, Olivia Galaxy NGC 474, is surrounded by several distinct shells of stars that were likely produced by collisions with other galaxies. Pretty crazy. So the idea would be you can have a bunch of stars kind of go towards the center and keep on going, and then kind of oscillate back and forth through the center, and so they bunch up at the extremes of their paths and make shells, as a matter of fact. Yeah, I'm going to keep going here with this. I'm going to keep going with this. Yeah, I want to talk about dark matter. So most galaxies have supermassive black holes in their centers. Like our Milky Ways is estimated to be about 4 million times the mass of the sun. Don't be under the impression that that means that it contributes a lot of our galaxy's gravity, because our galaxy has something like 400 billion stars, and a billion is 1,000 times a million. So the mass of the black hole, 4 million solar masses, is a tiny fraction of the mass of the Milky Way as a whole. And yet, cool, most galaxies seem to have a supermassive black hole near their centers. This is the most distant object I've ever seen with my eyes. This is the quasar 3C273. 3C stands for the third Cambridge catalog of radio sources that was compiled back, and I think it was at least the 1960s, maybe the 50s, but I think 1960s is when radio astronomy had come far enough to compile something like that. And it was noticed that that radio source was associated with, if you look there optically at the same location, there was what looked like a 16th magnitude star. Not terribly impressive. It just looks like a star. Don Stevens knows how to find it in the Perkins telescope, so when I was there one summer night with my students, he showed it to us. And so I've seen this with my own eyes. It's a quasar more than 2 billion light years away. So I've seen photons that are more than 2 billion years old, much older than humanity, much older than multicellular life on Earth, and so forth. Pretty cool. It just looks like a star, although what's this? It seems to be a jet of material thrown out from the center. Well, long story short, quasars are the centers of galaxies billions of light years away that have a big accretion disk around their supermassive black hole so that it is absorbing a significant amount of material and emitting X-rays because of the friction in that accretion disk. And furthermore, there are jets of relativistic particles, it turns out, shot out by the magnetic field perpendicular to the disk. And now we feel that quasars and other so-called active galaxies, the unified model says that they represent supermassive black holes with active accretion disks around them. There are no nearby quasars. 3C273 is the nearest quasar, and it's more than 2 billion light years from us. So what does that suggest? It suggests that the age of quasars ended around 2 billion years ago. The Milky Way isn't a quasar, but it might well have been in the past, but the supermassive black hole has already eaten its lunch. In other words, the accretion disk is gone. It's already eaten it, so to speak. And so we think that that's what happened, that quasars are only seen far away because only earlier in the history of the universe were there these large accretion disks around these central black holes, and now they've eaten their lunches. The accretion disks are largely gone. So every once in a while, the central massive black hole of our galaxy will burp and emit some extra light or whatever, but nothing sustained like a quasar. So that's pretty cool. And furthermore, 2020 Nobel Prize in Physics, Andrea Ghez got it for leading a team of astronomers carefully measuring orbits of stars around the central black hole. And here is actual orbits plotted between 1995 and 2014. Each dot is an observation of a star, and they were able to show that, essentially Kepler's laws imply a mass of almost 4 million solar masses in some little region at the center, and it's hard to understand what else it could be but a supermassive black hole. And furthermore, they were able to show that once you get very close to it, their orbits differ from Newtonian orbits in the way that is predicted by the Schwarzschild metric. Orbits are a bit different in the Schwarzschild metric, and they were able to show that. And so, cool. Get a Nobel Prize for showing that there's a supermassive black hole in the center of the galaxy, and you too can. That seems like fun, doesn't it? All right. Okay. A lot of you have seen this video already, so I'm not going to show it right now. Let's talk about dark matter and the OWU connection to it. And if you want to see that video, go on to the page, to the Blackboard, and click on the link. But anyway, a lot of you have seen. So there's like IQ talk from a few years ago, my mission talk just this weekend. In the 1930s, astronomer Fritz Zwicky measured Doppler shifts of galaxies and clusters of galaxies. And what he showed is they're moving fast enough that if you try to account for how much gravitational potential energy there is by estimating the masses of those galaxies based on the amount of light we can see, and assuming it's in stars, gas, and dust, and knowing the characteristics of stars, gas, and dust, turn that into an estimate of the masses of those galaxies, turn that into an estimate of the gravitational potential energy of the galaxy cluster. If it's stable, then there should be a relation between the gravitational potential energy and the kinetic energies of motions of the galaxies. Why that relation is something that we like to call our favorite theorem. It's the virial theorem. Zwicky showed that the virial theorem apparently doesn't apply, basically it looks like if you just sum up what you would estimate for the gravitational potential energy based on the mass you can see, it looks like these are not in virial equilibrium. There's too much kinetic energy relative to gravitational potential energy, which would mean they're going to fly apart. There's not enough gravity to hold them together. In a time much smaller than the age of the universe. Now, if you see something that still exists when it should have flown apart in much less than the age of the universe, what you conclude is something's wrong with the estimate of that gravitational potential energy. And so what it suggests is maybe there's a lot of mass that we're not seeing. So his observations in the 1930s were the first hint that maybe there's more mass in the universe than we can see. It was the first hint of the existence of so-called dark matter. How many of you know what the next slide is going to be already? Yeah, right. Anybody not know what it is? Okay, so you know my story, but it really is true. I'm not making it up. I really was. I was looking at this photo, I'm like, God, he reminds me of something. And all of it really did. I'm like, oh my God, he looks like an old bishop. And I'm like, ooh, this is gold. I can just like put this in a talk. And you know, even when I've shown this in other places, they still think it's funny because I guess they just infer, oh, that must be O's, you know, like athletics logo or whatever, you know. So I always assure them that on campus, this just kills. I mean, but I mean, it's amazing, you know, even like the hand on the shoulder and the kind of. But he apparently really did have that kind of personality that seems to be implied by that. Y'all have heard of the spherical cow approximation, where you say, well, you assume, right, it's a big joke where your famous physicist is hired to, like, you know, design a cow, I don't know, milking, trimming, or whatever mechanism. Big colloquium, and it starts by saying, now assume the cow's spherical. There's another version where it's a sheep shearing. You assume the sheep is spherical. Well, that joke goes way back, and Fritz Zwicky would refer to colleagues who he didn't respect because he thought that they were saying stupid things. He called them spherical bastards because they were bastards no matter what angle you looked at. So this is a good depiction of his personality, apparently. But then along comes Vera Rubin of the Carnegie Institution of Washington, who, along with W. Kent Ford, who had made a state-of-the-art spectrometer, decided to measure Doppler shifts of emission regions, i.e. H2 regions, in the Andromeda Galaxy, which, strangely enough, even though Hubble had shown long ago that it was the Andromeda Galaxy, was still, in 1970, when this paper was published, often still called the Andromeda Nebula, right, with the idea of it's just a nebula within our own galaxy. Everybody knew it wasn't a nebula, but still, spiral galaxies were often called spiral nebulae, even that, you know, at that point, long after they were known to be galaxies. Rotation of the Andromeda Nebula from a spectroscopic survey of emission regions, and of course, you probably also know that in section 2 of the paper, the DTM image tube spectrograph was used on the 72-inch telescope of the something like Ohio State or something like that, and universities at Lowell Observatory, and that for the Perkins telescope, the scale perpendicular to the dispersion is up to 40 arcseconds per millimeter. So she was using still our telescope at the time in Arizona, it moved there in the early 1960s, to measure this, to do the measurements in this really famous paper that got scientists to really take the idea of dark matter seriously. This is really what tipped the balance. And people were saying, wow, we really need to take this seriously. Here's the Perkins telescope at Perkins, and here it is in Arizona. If you go down to Perkins, you can see a photograph of the Perkins telescope with what I swear is Dr. Tree standing next to it in like the 1930s. I guess he's just ageless or something. Or maybe it's somebody else who was Question?
I asked Dr. Trees, it's not him.
It's not!
No.
He's lying to you. He doesn't want you to know about his deal with Beelzebub. Yeah, Yeah, he's lying, that's him, I swear it's him. Yeah, so, here, back in 2016, I went to visit Satoshi Inaba of Waseda University in Tokyo. He came here in 2009 because he wanted to, he's at SILS, the School of International Liberal Studies, he's now a dean there. At the time he was just a professor there. And SILS is supposed to be like a liberal arts college, so to speak, within the larger Waseda University, because they don't really have liberal arts colleges in other countries like we do in this country. So he wanted to learn about how like astronomy is taught at liberal arts institutions, and one of his exchange students from OU told him about our program here. He says, oh, okay, I'll visit OU. So we did back in 2009. We became friends. He did a sabbatical in 2016 when the AAS, American Astronomical Society, meeting was held in January there that year. He had told me he was going to be there, and I said, well, what a coincidence, I'll come visit you. And then since he had learned about the Vera Rubin connection with OU and all that, he was doing a sabbatical at the Carnegie Institution of Washington, Carnegie Institution for Science. And he, unfortunately, it was night, so she wasn't there, and she was still alive at the time. She died that year, but she was still alive. Here's her door at the Carnegie Institution of Washington, and here is her proudly displaying her measurements with our telescope of the Andromeda Galaxy on her door there. And what she discovered is that even very far from the center, the orbital speeds are very nearly constant. And the idea is, of course, that if the galaxy is rotating, and it is, right, one side's moving towards us, the other side's moving away from us, and so you can see red shifts on one side, blue shifts on the other, after you subtract off the overall motion of the galaxy. So she used that and saw that the red shifts were pretty constant, and the blue shifts were pretty constant, no matter how far you were from the center. So everything's going around at basically the same speed, except if you look at a photograph of the Andromeda Galaxy, the mass looks like it's strongly concentrated towards the center. And if you look at it visually with binoculars, it even looks more like that. I mean, the nucleus is way brighter than the rest of the galaxy. It really looks like mass is concentrated towards the center. A photograph undersells it because you overexpose the center in order to show the spiral arms well. And so it doesn't show just how much brighter the center is compared to the edges. Now, the Andromeda Galaxy is 3 degrees across on the sky. That's 6 times the size of the full moon. It's actually substantial in our sky in terms of how large it is. I once had to comment on somebody had posted a meme on a group saying that, like on Facebook, and people are like, fake news, that's all good. So I went on there and said, no, I'm a professional astronomer, and actually that is how big Andromeda would look in the sky if we could see it very easily with our eyes. Shut up. Anyway, point being that if mass was really concentrated towards the center, Kepler's laws would say everything should get slower and slower as you go away from the center. But instead, we don't see that, and our best explanation is that there's unseen dark matter. She and others, measured many, many more galaxies, and the story is always the same. Flat rotation curves, so-called, that imply the existence of unseen dark matter. And when we get to the next chapter, I'm giving you 3 minutes of education here, because I want to get to that chapter next, we'll see the evidence is that dark matter, there's about 5 times as much of it as the baryonic matter that you and I and planets and stars are made of. And it's not just rotation curves that say that. Here is a galaxy cluster, and these blue thingies here are all images of exactly the same galaxy far in the background that are due to gravitational lensing by the gravitationally curvature of space of the foreground cluster of galaxies. And you can calculate how much gravitational curvature is needed to produce this pattern of multiple images, and the result is consistent with there being way more dark matter than what you can account for by just adding up how much light is coming from all the galaxies and estimating how much mass there is in stars and gas and dust in those galaxies. And so that's what it comes down to, is that it looks like the kind of matter you and I made of is not the main form of matter in the universe. So there will be a homework problem where you estimate the density of dark matter in our part of the Milky Way. And a punchline, last thing I'll say here, a punchline I want to take away is, even though there's much more dark matter than baryonic matter in our galaxy and other galaxies, it's very spread out. It's spread out into a big dark matter halo that's much larger than the disk of our galaxy. And so in our location, don't be under the impression that there's lots of dark matter in this room. When you calculate the density of the dark matter from that homework problem, you can then turn it into an estimate of how much dark matter should be inside Earth based on that density. And the answer you should get is approximately 1 kilogram of dark matter within Earth. So in other words, locally in the disk of a galaxy, baryonic matter is absolutely dominant. Dark matter makes up in volume what it lacks in density. That's what it comes down to. It's very spread out, it's very low density, but there's so much volume that it occupies that it more than makes up for that in terms of the total amount of mass that we're talking about. But this room, Earth, the solar system, the disk of the galaxy, those are overwhelmingly dominated by baryonic matter. Well, I shouldn't say the disk of our galaxy, but, well, yeah, within the disk. But that dark matter halo, that spherical distribution of dark matter is what's causing the rotation curves to be flat. There's a lot of dark matter above and below the disk spread out in the dark matter halo. And that's what adds up. Within the disk itself, there's much more baryonic matter than dark matter. And emphatically so, like, when something is concentrated as a planet. Again, 1 kilogram of dark matter, compare that to the mass of Earth. What's bigger, a kilogram of dark matter or the mass of the Earth? Which do you think? What would you guess?
The Earth.
Yeah, the Earth. That's absolutely right. Because the Earth's mass, anybody know what the Earth's mass is, roughly speaking? It's 6.
6.7
Just go with 6.
times 10 to the 8.
Keep going.
26.
Too much.
12.
More. More than 21. More than 23. Less than 25. 24. 6 times 10 to the 24th power. 6 trillion kilograms is the approximate mass of Earth. That's a lot more than 1 kilogram of dark matter, just saying. All right, get out of here! What are you hanging out here for? Time to go. Oh, right. What's that? Yes.